All right, we're going to review what we did on Friday real quick. So x and y vary inversely when y is 10 and x is 1.5. Write an equation that relates x and y. So again, on Friday, inverse is y equals k divided by x. So I substitute in the numbers. 10 equals k divided by 1.5. To solve for k, I would multiply by 1.5. And k would equal 15. And then again, I need to write the equation. So this is where students will lose their points because they forget to write the equation. They think, oh, I solved for k, I'm good. You actually have to write y equals 15 divided by x. This is your equation that relates x and y. So do not forget to do that when we come to a test or a quiz. You'll also have a part B where it says now evaluate, let's say when x equals 3. So part B would be, okay, plug a 3 in for your x, and y would equal 5 would be the second half of that. Okay, that's what we did on Friday. Inverse variation, we talked about joint variation as well. Funny thing is it's only Tuesday, so I actually haven't taught you that stuff yet, but now that you're seeing the video, I have. So congratulations, we were in the future, in the past. Good times. All right, notes for today. Section 9.2, so we're going to graph rational functions today. We're going to graph rational functions. A rational function is just two functions being divided. P of x divided by q of x. What they look like, we call it a hyperbola. It's actually, it looks like two functions being graphed where we have a vertical asymptote. That's a dotted line that the graph will never cross. And we also have a horizontal asymptote. A dotted line, again, that the graph will never cross. So it's going to be the two pieces of the graph. They're always going to be in opposite quadrants of each other in our chapter. That's not a true statement overall. We only graph simple rational functions in Algebra 2. If you guys take pre-calc or go on to some upper level math, then you'll graph some things that graph in quadrant 1 and quadrant 2. But for us, they're always going to be in opposite quadrants. So quadrant 1 and 3 or quadrant 2 and 4. Things we have to talk about is the horizontal and vertical asymptotes. So I'll abbreviate those with VA and HA. A vertical asymptote is an x equals equation, and a horizontal asymptote is going to be a y equals equation. And those are going to be found depending on the form that the function is in. And we will have two forms today that we'll talk about. So those are just some things to look for. So we're going to get started right away, and we're going to graph. Again, our picture is going to look like that hyperbola, and we're going to start with what I call good form. Good form is in that, I'll give you a second to copy down, y equals 3 divided by x minus 1 plus 2. So this is just the form, again, that we've had all your y equals a divided by x minus h plus k, where the a value stretches it, flips it, the h value moves it left and right, the k value moves it up and down. The nice thing about this form is the h and the k, those are your asymptotes. So just like before, the vertical asymptote, x equals, and this would have a starting point if we thought of it as the vertex, it would be x equals 1. And the horizontal asymptote, again, our k value that we talked about, would be y equals 2. So it follows suit with everything we've talked about. X value is the opposite of what the number is. The y value is just what it is. So that's the first thing I start with, is I start at 1 and I put a dotted line. So there's my vertical asymptote at 1. And then I have a dotted line at 2. Horizontal asymptote at 2. And then what I actually do is I make an XY table. In years past, I had the kids learn a form when it's in what I call good form to graph it one way, and then when it's not in so good a form, then you graph it a different way. Instead, I just tell students, well, let's just graph it the same way every time so then you don't get confused. So what I have them do is you're going to make an XY table. You're going to pick 2 points to the right of the vertical asymptote. So my vertical asymptote is at 1. I'm going to pick the point 2 and the point 3, and I'm going to plug it in. So if I plug a 2 in, 2 minus 1 is 1. 3 divided by 1 is 3. 3 plus 2 is 5. So I plot the point 2, 5. So there's 2, 5. Then I'm going to pick a 3. So again, if I plug a 3 in, 3 minus 1 is 2. 3 divided by 2 is 1 and a half. 1 and a half plus 2 is 3 and a half, so 3.5. So I have the point 3, and 1, 2, 3 and a half. And that should be enough for us to get the general shape of that first piece of the hyperbola. It's going to follow the asymptote. It's going to go through those 2 points, and then again follow the horizontal asymptote. So that's the first half of it. Now you can do one of two things. You can make a second XY table and pick 2 points to the left. So I would pick 0 and -1. Or we can understand this idea of reflection. And we know it's going to be in quadrant 3, if you want to consider it quadrant 3, by our new dotted lines. From, I'll call that the origin of this new graph, I went over 1 and up 3. So I can go left 1 and down 3. And that's where a point will be at. I went over 2 and up 1.5. So I can go left 2 and down 1.5. And that's always going to hold true for these hyperbolas. So you do not have to do all of the work. But again, just to double check, I got -1 when I reflected the point. So I'm going to plug a 0 in and see what happens. 3 over 0 minus 1 plus 2. Well, I'm going to move that so we don't run out of room for our domain. 3 over 0 minus 1 plus 2. So 3 divided by a -1 plus 2. So -3 plus 2 is -1. 0, -1. That was actually the point. Again, if I plug a -1 in, 3 divided by a -2 is a -1.5. A -1.5 plus 2 would be 0.5. So again, -1.5. I find it easiest to always just reflect, and I'll show that in the next example as well. Okay, last thing we're going to talk about is domain and range. Domain and range is going to be very nice in this chapter. It's going to be all real numbers. And I'm going to double check and see if we have to write this all reals. I don't recall. I think we got away from it. But this idea of x is all real numbers such that x cannot equal, and the nice thing is it can equal a 1. If I plug a 1 in to that original function, 1 minus 1 is 0. In math, you cannot divide by 0. So that's the one number that I cannot use. So that's why it's all real numbers except for 1. It's the only number you can't pick. And the range is going to be all real numbers such that y cannot equal. And if you guessed 2, you are correct, because there's no way when I plug those numbers in, this fractional piece at the beginning here will never be 0. So I can never get 0 plus 2. If you notice, the vertical asymptote and your domain, the horizontal asymptote and your range are going to be very, very similar. They're actually the same numbers all the time. One of them is equal to, one of them is not equal to. And you just got to make sure you keep them straight. So, second example. Again, another one in what I consider good form. So where we started before, x equals 4 is my vertical asymptote, and y equals 3 is my horizontal. So that's the first thing I graph. Vertical at 4, horizontal at 3, and if I'm making my XY table, I'm going to plug in 2 points to the right, so I'm going to do 5 and 6. And that's actually all the work I'm going to show this time, and I'm just going to reflect the other 2 just like I talked about in the last example. So if I plug a 5 in, 5 minus 4 is 1. Negative 1 divided by 1 is negative 1. Negative 1 plus 3 is 2. So I have 5, 2. If I plug a 6 in, 6 minus 4 is 2. Negative 1 divided by 2 is negative 1/2. That's going to give me 2.5. So 6 and then 2.5. Again, those are enough. I'm really close to those asymptotes on this one. So again, I just follow with the graph. Now I'm going to reflect again from the intersection of those asymptotes. I went right 1, down 1, so I'm going to go left 1, up 1. I went right 2, down 1/2, left 2, up 1/2. And there's the other half of my hyperbola. There's my graph. Again, if I come to the domain, x is an element of the reals, such that x cannot equal, the vertical asymptote on this one is 4. The range, y is an element of the reals, such that y cannot equal, and in this case, it will never equal 3. It's going to get really, really close to 3, but never actually touch it, and that's actually your foundation for limits. But that's calc. So, good form, find the h, find the k, plug them in, you're good to go. Here's what the other form will look like. ax plus b over cx plus d. Hopefully you noticed on this one that there are two x's. There's an x in the numerator and an x in the denominator. On the first form, there's only an x in the denominator. So that's how you're going to tell the difference between the two forms. So here, your vertical asymptote. Vertical asymptote is when the denominator is 0. It's going to be just a little extra work. You've actually done all this stuff before. If you had something that looked like this, you would tell me that the intercepts are at -4 and the intercept is at 1/2. You would add 1, divide by 2. It's the same thing you do for the vertical asymptote. You just take your denominator and solve for x. So in this case, x would equal subtract d, divide by c. So negative d over c. The horizontal asymptote is easier math. You just look at the coefficients. Well, I gotta change the highlighter there. It's the coefficients on the x's. So this one, my horizontal is y equals whoop. Let's try that again. Oh, it's going crazy, folks. See if we got it fixed now. Okay, should be good. Y equals a divided by c. I don't know why that keeps popping up, but again, vertical asymptote, set the denominator equal to 0 and solve, so it's just like you did when we were factoring in the last chapters. Horizontal asymptote, ratio of the coefficients. So here's what one of these look like. X minus 2 over 3x plus 3. So I start the same process. Find the vertical asymptote. So in this problem, my denominator, 3x plus 3. So off to the work, or off to the side, 3x plus 3 equals 0. Subtract 3, divide by 3, x equals -1. Vertical asymptote, x equals -1. Horizontal asymptote, y equals, there's a 1 out in front of that x, so it's 1 over 3. It's the ratio of the coefficients. If you want to fill in your domain and range right away, you can. X is an element of the reals, such that x cannot equal -1. Y is an element of the reals, such that y cannot equal 1/3. So I start by graphing those. -1 for the vertical asymptote. 1/3 for the horizontal asymptote. Plug in 2 to the left, 2 to the right. So I'm going to go 0 and 1. So if I plug a 0 in, -2 divided by 3. So that's -2/3. If I plug a 1 in, -1 divided by 6. That's a -1/6. So 0, -2/3. Maybe right about there. 1, -1/6. I'm going to go just below the axis there. That's enough for me to draw the first half of my hyperbola. Now, this might be a little difficult for people to figure out with the fractions, how far away to the right and down am I? And then, again, 2 spaces away, how far down did I go? So on this problem, you may just want to pick 2 points to the left. So what do I get when I plug a -2 in? What do I get when I plug a -3 in? If you're not good with fractions when you're doing that. So plug a -2 in. -4 divided by -6 plus 3. So -6 plus 3 would be -3. So that would give me a positive 4/3. So -2 and then 1 1/3. Did I do that math right? Nope. Let's see. -2, so -2 minus 2 is -4. -6 plus 3 is -3. Okay, yeah, so we're good. I thought that was going to be a whole number, but nope, we're good. That checks out now. Plug a -3 in. -5 over -9 plus 3 is -6. That'd be positive 5/6. So -3, 5/6 is just below 1. Again, if I draw my hyperbola, it's going to go through those points, follow along, and we're good. So when it's in the form where it's not as convenient, you're going to have to work a little more with some fractions maybe when you get your answers. And again, on the bottom there, if you guys can see, as you approach infinity, the graph approaches a divided by c. That's just the limit definition in calculus. As I go off to infinity, it eventually will approach a divided by c, but it will never actually equal it unless you start talking about limits, but that's something different. Excuse me. All right, last thing, you got a word problem. You're going to have one question like this, if I remember correctly, on your test. So you have to know how to do these. There's 2 of them in your homework tonight where you practice this process of setting up an equation and then solving it. So it says the senior class is sponsoring a dinner. The cost of catering the dinner is $9.95 per person plus an $18 delivery charge. Part A says write a model that gives the average cost per person. So I got to figure out average cost per person. So y equals, if it's $9.95 per person, then it's going to be $9.95 times x plus, there was an $18 delivery charge. So that you'd have to pay 18 bucks up front. So plus $18. That would be my total cost for everybody that showed up. To find the average cost per person, to find average, I have to divide by the number of people that were there. Well, if we don't know how many people are coming in, then we don't know how many people were there. So I'm going to divide by x. And what that does is that sets up my average cost model. Total cost, $9.95 times x plus 18, divided by how many people came in, which was, again, x. So the number of people and the number of people are going to be the same. So you're going to have an x on the numerator and the denominator. Part B says graph the model and use it to estimate the number of people needed to lower the cost to $11 per person. For time's sake, we're going to skip that. We're actually going to do it by algebra later on in the chapter. But you could punch that into your calculator and put in y equals 11 and just look for the intersection. I don't remember how many people it is, but it's that kind of idea. So we'll get to that later. So this is part A, the equation. Part B we'll skip. Part C says describe what happens to the average cost per person as the number increases. So as we approach infinity, as we have more and more people show up, this idea of $9.95 per person per plate plus $18. So if I broke this up into 2 fractions, and again, this is what we used to do in calc. But this idea, this first one, 995x divided by x, my x's would cancel out. And then here, nothing would cancel out. So as I approach more and more people, the $9.95 per person is going to be $9.95. The $18, as I get more and more people to show up, that price gets distributed amongst everybody. So if 100 people show up, it's going to be 18 cents more for each person. If 1,000 people show up, it's going to be about 2 cents more per person. If 10,000 people show up, there's basically that $18 delivery charge is gone. So it's $9.95 per person. If you look at what we talked about, the horizontal asymptote is the ratio of the coefficients. $9.95 divided by 1. The average cost per person as we get more and more people to come to the supper is going to be $9.95. That $18 delivery charge won't mean anything if 1,000 people show up. The average cost per person is going to be $9.95. All right, so that is graphing. There's two methods, again, two forms you're looking at. The what I call good form, A, H, and K, and then the one where you have the ratio of the coefficients. So make sure you understand the difference between the two. Your book assignment tonight actually breaks it up into two sections where you're going to see all of the good ones are clumped together in the assignment, and then all of the what I call non-good ones are clumped together. And then, like I said, you have two word problems. Number 10 is a word problem, and I believe 42 and 43 are one word problem but two separate questions. All right, so go ahead and get started on your homework. Graph paper is up on the table where it normally is if you want some graph paper for tonight.